Hello, Math 311. Here is the intro video for linear algebra. I'm going to go over the first two sections of the textbook, which is a really just kind of crash course in linear systems. And so without further ado, let's start. So first thing we need to talk about is what is a linear equation. We've already discussed this a little bit, but the idea is that you have some variables, x1 through x of n. We're going to use subscripts just so if we need a lot of variables, we don't run out of letters. So those are going to be our variables. And then the A1, A2, AN, and B. So the A sub I and the B are called coefficients. For differential equations, those are allowed to be functions of t. For the purposes of linear algebra, these are just going to be real numbers. These are real or complex numbers. They could be complex numbers too. And so the idea is a linear equation is just a sum of a bunch of, where is my laser at? It's a sum of the variables times a bunch of coefficients equaling a variable. These numbers can be zero, by the way, too. So they don't all have to be like a non-zero number. So you might not have all the variables represented, but those are the coefficients, and then those are the variables. A system is where you have multiple of these linear equations at the same time. Also, another way you can think about these things geometrically is, for instance, an example is like this x plus 2 x1 plus 2x2 plus 3x3 equals 4. This is the equation of a plane, where instead of using x, y, and z, right, this could have been x plus 2y plus 3z, but we're just going to use x1, x2, and x3 instead. And so those are equations of a plane. And so the idea is that we can ask, well, what about when they intersect? And so what does that mean? That means when do all these planes get satisfied simultaneously? And so to do that, that gets what's called a system of linear equations, or a linear system. And so here's an example. And this would be, so 2x1 minus x2 plus 1.5x3 equals 8, and this. And so you see that the x2 coefficient is 0. And this would be an example of, geometrically, you can think about this as two planes. That's the equation of plane, that's the equation of plane. And the system would be, okay, what is the equation of their intersection? Like what points satisfy both equations simultaneously? And so system of linear equations come up, really, they have so many applications. But for our purposes, we're not going to get into too many of the details of that, but they do show up in everything. For our purposes, though, when we look at a linear system like this, there's kind of some questions that come to mind, like what is a solution? So what is a solution? A solution is a point S1, S2, dot, 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 Sn, where S are just real numbers or complex numbers, or they're just numbers. Is a point that satisfies all equations in the system. And so sometimes you can have one solution, sometimes you can have multiple solutions, sometimes you can have no solutions. And so a system of linear equations has, those are the only three options. Either there's no solution, so there exists no point, i.e., for instance, if you think about two planes, maybe the two planes never touch each other, so then that system of equations has no solution. Or there could be exactly one solution. In the example for two planes, that's actually only possible if for two planes, you'd actually need three planes to be exactly one point, but we'll get to that later. But with two planes, they're either going to intersect in a line, or they're going to intersect everywhere, or they're going to not intersect. And so that's actually not possible. You can't have a unique solution. And then, or there's infinitely many solutions. For instance, if the equation, we found the equation of the intersection of these two planes, that would actually, I think it'd be a line if I'm not mistaken, yeah, because they're not the same plane. And so it'd just be a line, and they're not parallel to each other. And so it'd just be a line. And so that's infinitely many points, because a point has infinitely many lines. A line has infinitely many points on it. And so a system is consistent if it has one or more solutions. It's inconsistent if it has no solutions. This terminology will make more sense when we get to the matrices, but consistent basically means there is a solution. Inconsistent means it's not possible to have a solution. So an example of an inconsistent system would be like x1 plus x2 equals 2, and x1 plus x2 equals 4, because that would require that if you kind of added these two things together, these are kind of parallel lines, and if you kind of graph them, they would never run into each other. So this is inconsistent. This is inconsistent. The other way you could do this is you could subtract these equations, and you get that 0 equals 2, I guess, if you subtracted them, or 0 equals -2, and that doesn't make any sense, and so this is inconsistent. So solving systems like this, maybe you, when you only have two equations and two unknowns, you could like do substitution and try and do that. And so that's something maybe you learned in the class. And so you'd be like, oh, x1 equals 2 minus x2. Then you would like you'd plug this in for x1 right here. And then you get 2 minus x2 plus x2 equals 4, which that leads to the equation 2 equals 4. But that's a contradiction. That's not possible. So you can't have that. So that's why it's inconsistent. The issue is, what if you get really complicated systems? So this is, I mean, even this system's not that hard. You could probably solve it by doing substitution. But what about when you have way more equations or way more variables? And that's where this next technique, which is kind of the genesis of linear algebra, comes from. And that's what's called coefficient matrix or matrices. And so what's the idea here? We take a linear system. So it's a system of 3 equations. There are 3 variables, x1, x2, and x3, that show up in the equations. And so we're trying to find some solution to this. And the idea is that there's kind of 3 operations you can do to this. You could add rows together, you can swap rows, or you can multiply a row by a scalar. So those are kind of the row operations. So these are what are called row operations. And so the 3 row operations are, you can swap rows. So that's something we can do when you have a system of equations, and that won't affect anything, right? I can just switch the order of the rows. The other thing I can do is I can add, or I can scale a row, multiply a row by a scalar, c, so just a number, c. That doesn't affect the linear system, and so I can multiply this whole row by 3, and that doesn't do anything, or multiply this whole thing by 1/2, and I get x2 minus 4, x3 equals 4. So I can multiply a row. And then the third and probably most important row operation is adding a multiple, like a scalar multiple, of a row to another row. And so this is what a lot of times we call elimination. And so it's the elimination technique in a system of linear equations. And so you add some of this row to this row to like eliminate a variable, with the idea that we can kind of break it down and try and get to a solution, like a single point that satisfies it. It turns out that these 3 things that you can do on a linear system correlate to what you can do to just their coefficients. And so we're going to ignore the variables, and we're going to create this matrix called the coefficient matrix. And so what is a matrix? A matrix is an array of numbers that has rows and columns. The number of rows are going to be the number of equations, and so we have 3 rows. And then the number of columns will be the number of variables. And then for the equal sign, I'm going to put a line, what's called an augmented matrix. And then I'm going to have the solution on the left. The book doesn't do augmented, but that's fine. So this coefficient matrix will be 1, -2, 1, and then 0. And it will be 0, 2, -8, 8, and then 5, 0, -5, 10. And I like to put a little line here to let me know that this is the coefficients for like the linear system, and then this is the solution, or like, sorry, what it's equal to. So this is called an augmented coefficient matrix. So this is an augmented. The augmented part is this line right here, augmented coefficient matrix. And it turns out that all the stuff that we can do here to try and find a solution can be done here. And it actually is much simpler when you do on a matrix. And even if that was all linear algebra, that'd be pretty powerful, but there's actually way more that you can do with linear algebra based on actually what these coefficients are, but we'll get to that later. But I'm just going to show you how to row reduce a matrix. And so what we're going to do is we're going to do some row operations on this. And so let's start with our matrix, our row reduced matrix, copy. And I'm going to, so I just like to draw arrows like when I do something. Let's add, so a lot of times books write it like this, like row 3. So, oops, there should be an R. Row 3 is going to equal, I'm going to replace it with row 3 minus 5 times row 1. And so I'm replacing that row. Actually, maybe I should scale it first. That'll make it easier because it actually is very nicely divided by 5. And so row 3 divided by 5. So 1/5 of row 3. And so that gives me the matrix 1, -2, 1, 0, 0. I'm also going to do 1/2 of row 2 just to rescale that and put ones here. The reason for that will become a little bit more clear when we get to reduced row echelon form, but for now, it's just to make our algebra a little bit easier, or our addition. And now I can take this and try and eliminate that variable. And so what I'm going to do is I'm going to add. So row 3 is going to equal row 1. I guess that's row 3 minus row 1. Row 3 minus row 1. And so if I replace row 3 with row 3 minus row 1, 0, 0, 1, -4, 4, and then 0, if I subtracting 0 from -2 means adding 2 times a 2, subtracting -1 from 1, or I guess subtracting 1 from -1 gives me a -2, and then augmented with, and then subtracting 0, this would still be 2. And then I can add 2 more of row 2 I can use this one to eliminate that position right there. And so that's row 3 equals row 3 minus 2 row 2. So if I subtract 2 of those, this is 0, 1, -4, 4, and this will be 0, 0, and then -2 times 4 is 8 minus 2, so it's going to be 6 here. And then 4 times -2 is -8, and 2 gives me -6. And so from this is almost in the right form. I can reduce this down a little bit more, and then it will get me, so I'm going to just divide 1/6 row 3. You don't have to write down what you do every time. I'm just doing it in the first time so you can get used to it, but generally I don't write it. I just kind of do the operations as you get used to it. -4, 4, 0, 0, 1, -1 from there. And then I can revert this back to a system. So this is x1 minus 2x2 plus x3 equals 0. X2 minus x4, sorry, not x4, x3, minus 4x3. Minus 4x3 equals 4. And then finally, x3 equals -1. And then, now that I know that x3 equals -1, I can plug that in here and figure out what x2 is. And then once I know what x3 and x2 is, I can plug that in and get x1. And so I think you get a unique solution. I don't actually know what the solution is. So if x3 is -1, then that means x2 has to be 0. So this implies that x2 equals 0. And if you get 2 and 0, that means x1 is also 0. So this one will also be 0. x1 equals 0. And so does that satisfy all 3 of the solutions? Shoot, no, something went wrong here. What did I do wrong? 4 minus 4, so x2 is 0. 0. Oh, x1 is going to be 1, not 0. X1 has to be 1 to cancel out that. So x1 is 1. So the solution, it's a unique solution, is 1, 0, -1. And so that's the unique point of intersection of all 3 of these planes. Those planes all intersect at this unique point, 1, 0, -1. And you can make sure that that works. If I plug in 1 for x1, -1, that works. That will give us 10. If I plug in 0, -1, that works. And if I plug in 1, 0, -1, it also works. So this is the solution, and it's the unique solution. And so 2 fundamental questions about linear systems. Is the system consistent? Does it have at least one solution? This one is consistent. If a solution exists, is there only one? Is it unique? And so these are really, really important questions in linear algebra and differential equations. Is there a system, or sorry, is there a solution? Is there something that'll satisfy it? And if so, is that solution unique? So it's kind of the existence uniqueness question. And so for our last system, so for above system, it is consistent, and it is unique because there's only one solution. There's only one number for x1, x2, and x3 that satisfies all 3 equations simultaneously. And the idea was we kind of took this system, translated it into a matrix to kind of record all the coefficients on it. And then we did these 3 row operations, swapping. We didn't really swap rows, but we multiplied a row by scalar and we added multiples of a row to another to try and reduce it down to a simpler system. And then with that simpler system, we can get the solution. And then, yeah, and so let's see if this system is consistent. We're going to do the same technique. And so we're going to convert it to a matrix. So the matrix will be 0, 1, -4, 8, 2, -3, 2, 1, and then 4, -8, 12, 1. And so that's the augmented system we're going to work with. I probably am going to want to swap rows. And so this, I'm going to swap rows. So swap R1, R2, and I'm going to probably scale it. So it's a 1. So it's 2. Maybe I can just do it in steps. It's okay. -2, 3, 2, 1. 0, 1, -4, 8, 4, -8, 12, 1. Then what I'm going to do is I want to add 2 of this row, or subtract 2 of that row from that row. I'm going to make this over to the side so I have room. And so I'm going to replace row 3 with row 3 minus 2 row 1. That way I get the 0 there, so it's 2 minus 3, 2, 1, 0, 1, -4, 8. And then this will become 0. -2 times -3 is 6. Added to -8 gives me -2. And then -2 times 2 is -2 times 2, sorry, -4. 12 minus 4 is 8. And then 1, -2 gives me a -1 here. Then I'm going to take this number to eliminate that one. So I'm going to add 2 of row. So row 3 equals row 3 plus 2 row 2. So I get 2, -3, 2, 1. And then I get 0, 1, -4, 8. And then if I add 2 of it, I get 0, 0, and then another 0. And then 2 times 8 is 16 plus 1 is 15. And so this leads to an equation on the bottom. 0, 0, 0 equals 15. And so this bottom equation, or I guess I can write the whole system as 2x1 minus 3x2 plus 2x3 equals 1. x2 minus 4x3 equals 8. And then this bottom equation will be 0 plus 0 plus 0 equals 15. But that doesn't make sense. That's not possible. And so I like to write it like a contradiction. So this is inconsistent. And once you get a equation of all zeros equaling a number, so zeros in the coefficient part and then the augmented part is a number, then we automatically know that it's not possible. There's no solution. So inconsistent, no solution. No solution. Okay, so that's the basics of kind of linear systems. And now to kind of record all this in a very consistent way and to kind of give it an algorithm, we're going to teach you the row reduction and echelon forms. So this is a lot of times referred to as RREF, reduced row echelon. Oops, that should be an F. RREF is reduced row echelon form. So this is this word right here, reduced row echelon form, RREF. Also, this process of reducing things down, a lot of people call this Gauss-Jordan elimination. So this is a way of dealing with linear equations or linear systems, and the way of kind of eliminating variables is called Gauss-Jordan elimination, but they don't call it this, but that's what it is. What's the idea? We're going to take our augmented matrix and we're going to put it into this form called echelon form, where all non-zero rows are above any rows of all zeros. Each leading entry of a row is a column to the right of a leading entry of the row above it. All entries in a row in a column below a leading entry are zeros. And if you do some other stuff, you can call it reduced row echelon form, RREF. The leading entry in each non-zero row is a 1, and each leading entry is the only non-zero entry in its column. So let me give you some examples. So a matrix that's in echelon form, you go to the first non-zero column, and you use this, what we're going to call a pivot, which I'll define in a sec, and then that will zero out everything below it. Then we go to the next non-zero column and the next row. So we're gonna not focus on this row because this is the pivot for that row. And then this one we're gonna use to zero out those, and it doesn't really matter what's above it. And then there's no more. And then we go to the next row and we look for the first non-zero entry, and there's none. And so this is as far as we can do it. So what do we notice? All the non-zero rows are above the rows of all zeros. Each leading entry is in a column to the each leading entry of a row is in a column to the right of the leading entry of the row above it. So this is the leading entry. So the next one has to be to the right of it. And if there's another one, it had to be to the right and to the right. All entries in a column are below a leading entry of zeros. All entries in a column below are 0. Yeah, so if you have a leading entry, so that's what these squares are. Those are the leading entries. They're always zeros below them. And so this is echelon form. And so it kind of has this like little pyramid-like thing, and there's always zeros to the bottom left of it. And then to reduce it all the way, so to take this and go reduce row echelon form, make that a 1, make that a 1, and then use that 1 to eliminate that, but then this could be anything. So these are called pivots, and we'll define them in a second, but they're the leading entries. Make them all 1s, and then use those 1s to eliminate everything above them. And so this would be the reduced row echelon form. Something that's actually really, really important about reduced row echelon form, about a matrix, is every matrix is row equivalent to 1 and only 1 reduced row echelon form. So what does that mean? That means that the reduced row echelon form is kind of unique for every system. So every system, every linear system has only 1 reduced row echelon form. So that means the solution to the reduced row echelon form is the solution to the system, and vice versa. And so that's really important. And so that means that this is how we can actually solve it. This gives us the way to solve it. These leading positions I've been talking about, these are called pivots. It turns out that pivots are extremely important for lots and lots of kind of theoretical aspects of a matrix, but for our purposes, they're going to be the things we use to kind of eliminate the columns below and above. And you always want your pivots to end up being 1 in reduced row echelon form. A pivot column are the columns that have pivots, and so those would be our pivot columns. And so this has 1, 2, 3, 4, 5 pivot columns. And you'll notice that the number of pivot columns is also equal to the number of pivot rows, if we define such a thing. A pivot row would be a row that has a pivot in it. And so this one has a pivot in every row, but not a pivot in every column. Whereas this one has a pivot in only 2 columns and not a pivot in every row. And so looking at this, if this was augmented matrix, like we augmented it with zeros or something, then would this have a solution? And this one would have a solution, and this one would have a solution. But if this was augmented with something that didn't have zeros, for instance, like 0, 0, 1, 1, then because these rows of zeros, it would not hit it, and so there would be no solution. And so that's what we got for that. One sec. Okay, so there's an algorithm basically using these pivots to always get any matrix into its reduced row echelon form, and that will give us a solution. So we're going to follow that for this particular matrix right here. And I don't want to keep writing it, and so I'm just going to copy this, copy, paste it. Oops, I just want the image of it. Paste image. Okay, so here's our matrix. So the step one, begin with the leftmost non-zero column. This is a pivot column. The pivot position is at the top. So here is our pivot column. Should probably actually circle this. So pivot column, and then our pivot is the highest non-zero point. So here's our pivot. That's going to be our pivot, but we need to put it at the top left. And so select a non-zero entry in the pivot column as a pivot. If necessary, interchange rows to move this entry into the pivot. And so doing that, I need to get this into position. So what I'm going to do is I'm going to take that pivot column and I'm going to switch the rows 2 and 3. So it becomes 3, -7. So swap row 2 gets swapped with row 1. So I'm swapping them so that I get the pivot. -6. Oh, sorry, that's not right. Row 2 is -8, -5, 8, and then augmented with the 9 over here. And then this will be 0, 3, -6, 6, 4, -5, and then 3, -9, 12, -9, 6, 15. So this is our pivot. This will be the pivot. So I swap the rows to get the pivot in the top left. Use row replacement operations to create zeros in all positions below the 0. So I'm going to eliminate that position using our new pivot. And so I think I just have to take this and copy it. So I'm going to use that to eliminate the next one. And so what's that going to do to this? This will go away. I'm going to subtract. So I'm going to subtract row 3 equals row 3 minus row 1. And so that gives me a 0. So I can erase this whole bottom row because it's all going to change. It's going to give me a 0. Then -9 minus 7. Minus -7 is plus 7, so -2. Then 12 minus 8 is 4. -9 minus -5 is -4. And then 6 minus 8 is -2. And 15 minus 9 is 6. And so that gives us our first pivot column with zeros below it. And then now the next step is cover or ignore that row. So we're going to ignore that row now. And then looking at this new submatrix, find the next non-zero column. And that will be this one. So this is going to be our new pivot column. And so let me take this. Oh, what the heck? Oops. So that's our new pivot column right here. So this is the next pivot column right here. So pivot column. That's the next one. And then we're gonna use that to get a new pivot right here, because we're gonna look at this next entry, and so that's our new pivot, and we're gonna use that to eliminate that guy. So this becomes a little bit more difficult because now we're gonna start getting fractions. So it will be R3 is gonna equal R3. How much? I have to R3 and then plus 2/3, I guess. 2/3 of R2. Yeah, so I have to start doing fractions, which is kind of annoying, but that's what we're going to do. 1 sec. Okay, sorry. Let's finish this. So it's 3, -7, 8, -5, 8, 9, and then 0, 3, -6, 6, 4, -5, and now we're gonna have to add some fractions. Oh, I don't love this. Woof. Okay. So 2/3 of row 2. So divide that by 3, I get 0. Divide that by 3, you get 2, and then times by 2 is -4, so that's going to give me a 0. And then that'll also give me a 0. And then 8/3 minus 2, whatever 8/3 minus 2 is. 8/3, I guess I just write it, minus 2, that's fine. And then -10/3 plus 6. I'm too lazy to actually figure out what those numbers are. Okay. And then repeat the process until there are no more non-zero rows to modify. So I think we're actually almost there. So the final step would just be to figure out what these numbers are. So this would be 8/3 minus 2. I think that's going to be 2/3. Because that's going to be minus 6. Yeah, so this is just 2/3. Let me just copy this and simplify it. No. Okay, so this is going to be 2/3. 2/3. And then -10/3 plus 6 is going to be 18/3 minus 10, so 8/3. I think it's just 8/3. And then I could rescale that and make that a 1. But this is in, so this is echelon form because I have a pivot. So let me circle the pivots. I have a pivot, and then the next pivot would be here. And so here's my pivot column, pivot column, pivot column, pivot column. So we have 3 pivot columns, 3 pivots. And then to find this gets it into echelon form. And so we could back solve from there. But now what we can do is we can actually make all these 1s and then get rid of the rest to simplify it down. So these are pivot columns, pivot. So the final step would be to get this into reduced row echelon form. And so to get into reduced row echelon form, we need to rescale all of them. So I'm going to rescale by dividing all the rows by 3s. And I guess I will rescale this by multiplying it by 3 halves. So this gives me a 1, -7/3, 8/3, -5/3, 8/3, 1, 0, 1, -2, 2, 4/3, -5/3. And this will be 0, 0, 0, 0, 1. And then 3 halves will be, I think that's 4. And so this is the reduced, not quite the reduced echelon form. I now need to take this and back to make those zeros and take this and make that a 0. And so that would look like 1, -7/3, 8/3, -5/3, 8/3. Oh wait, but I'm adding to this one. I'm gonna add -8/3 times this plus this to make that a 0. Or maybe, I guess, yeah, I'll 0 out them separately. And so this will be a 0. I need to make that a 0. And so -8/3 times 4. So it's 1 minus, this is where the algebra gets a little annoying, minus 8/3. So 32/3. Oof, okay, that's gross. And then 0, 1, -2, 2. And then -3/4. Or no, sorry, -4/3 times row 3. -4/3. And so it's -5/3. And then I have to do plus 4 times -4/3, so minus 16. thirds. Oof, okay, that is pretty brutal. But then 0, 0, 0, 0, 1, and then a 4. And then the last step, but actually this simplifies nicely. That becomes minus 7. Minus 7. This, I don't think, simplifies nicely. But then I need to add 7/3 of this row to that row. And that's the final step. And so I'll get a 1. And then 7/3 is going to be 0. 7/3 times this plus this will be negative 14 plus 8 is negative 6. So negative 6/3. So I think it should be negative 2. And then multiplying that by 7/3, or sorry, yeah, by negative 7/3 and adding it gives me 14. And then negative 14 minus 5 is minus 19. Well, that's a bummer. It's not a perfect third, but okay. Negative 19/3. And then this will still be 0. And then what is this? This is equal to negative 29/3. And so negative, and then this is equal to negative 21/3, which is negative 7. So negative 7 times negative 7/3 is going to be 49/3 plus 29/3, or negative 29/3. So I think it should be 20/3. It's very possible I made a mistake here, but I'm trying my best. This is why computers are way better at this, but everyone has to do it by hand once. But yeah, definitely computers are way, way better for this, and using a calculator definitely helps too. And then like that. So that is the reduced row echelon form for this one. And so from this, we would be able to find the solution pretty easily, I think. We get that x5 would be 4. This tells us that, what does it tell us? This tells us that x2, okay, so x1, x2, x3, x4. Do I want to do this? No, I think we'll just do it in this one. So this was just the steps on how to get into reduced row echelon form. And so this is the reduced row echelon form matrix. We can find the solution, but now let's do it with a none, but I think it's hopefully nicer. And so we're going to take this and we're going to get this into reduced row echelon form to find the general solution of linear systems whose augmented matrix is reduced. So what we're going to do is, actually, there's a couple ways to do it. You could from here, and so this is an augmented matrix where those are the things it's equal to. We could just start back solving in, or we could make it into reduced row echelon form first, and then start back solving. I think that's the plan. And so let's make it reduced row echelon form. So R, R, E, F first. And so I'll get a 1, a 6, 2, a negative 5. And then I'm going to add 2 of this to that. And that gives me 0. And then 2 times 7 is 14. So that gives me a 10. Then 0, 0, 2, negative 8. And then I'm going to add this row to this row. And that gives me a 0. And then that gives me a 10. And then 0, 0, 0, 0, 1, 7. That's almost reduced row echelon form. The final step would be to make this a 1 to eliminate that. But actually, I can just add it first and then rescale it because it already is so close. And so let me just add it. So you get 1, 6, and I guess I subtract it. So row 1 equals row 1 minus row 2 is what I'm doing there. So you'll get a 0, 3, 0, and then 0. And then this is 0, 0, 2, negative 8, 0, 10, and then 0, 0, 0, 0, 1, 7. And then the final step is I would just rescale. So row 2 divided by a half to put in reduced row echelon form. 1, 6, 0. Actually fits. 1, 6, 0, 3, 0, 0. 0, 0, 1, negative 4, 0, 5, and then 0, 0, 0, 0, 1, 7. Okay, so once I have a reduced echelon form, now we're going to write this as a system. So make it into a system. And so it's x1 plus 6, x2 plus 3, x4 equals 0. X3, I should leave gaps for where the variables are in here so that it all fits. So this would be x3 minus 4x4 equals 5, and then x5 equals 7. And so how do we get a solution from this? And so it turns out there's going to be a lot of solutions. So x5 is 7. And then this is telling me that x3 and x4 have a relationship. And so I could back solve for x4 in terms of x3 and get that here. And then x2 will be another free variable. And then I can get x1 in terms of that. And so this is what's called the parametric representation of that. And so let me move all this stuff down so we can get to that. And so another way to look at it is this from the matrix, this variable is determined because that's telling me that it has to equal that. This is telling me that this and this are going to be in some relationship. And so one of these I can just pick to be anything, and then I can get the other one written in terms of that. And then once I have that, I can put those up here and do the same thing. And so let me actually just write that. So x5 has to be 7. This equation, I could do it two ways. But because x4 is up here, I should probably get x4 in terms of x3. Although I guess it doesn't really matter. If I get x3 in terms of x4, I could just plug that in over here. But let's get x4 in terms of x3. So 4x4 equals x3 minus 5 by adding this guy over here and subtracting that guy over here. And so what does it tell me? That tells me that x4 equals 1/4 x3 minus 5/4. So that's what x4 is going to be. And then if I plug that in for right here, plug that in right here for x4, and I get x1 plus 6x2 plus 3 times 1/4 x3 minus 5/4 equals 0. Then I can get x1 in terms of x2 and x3. And so then what do we get? Solving for that, we get that x1 equals minus 6x2. And then what will that be? 3/4 minus 3/4 x3 minus 15 fourths. Oh, but plus, because I distributed it. Plus. So that's what x1 is. And now we can kind of just work our way down. So x2 can just be anything because x2 shows up here. And so x2 is just a free variable. So x2 is what we call a free variable. Free variable. Because x1 can be written in terms of x2 and x3, but then x2 doesn't show up anywhere else from our system that we reduced down. Then from this x4, x3, we've decided to make our free variable as well, because x3 shows up in the solution for x1. And so x3 is also what we call a free variable. Free variable. And then x4, well, we wrote down what x4 is. x4 is this. And so x4 is 1/4 x to the third minus 5/4. And then x5, well, we know that x5 has to be 7. And so the idea is that this is our solution set. So let me move that over. This is our solution set, but this isn't actually a super helpful way to think about our solution set. So this is the solutions. So solution set. And so what we want to do is we want a parameterized way of viewing this. How do we and so what we do is we call x2 a variable, we call x3 a variable. And so I'm going to call x2 s, and I'm going to call x3 t. And then I'm going to plug s and t into here, and I'm going to get a parameterized version of this. And why that is will make sense when we get to vectors next time, but I want to rewrite it as x1 equals negative 6s minus 3/4 t plus 15/4. So actually, let me not do this yet. And then so x2 is s, x3 is t, where s and t are just any numbers. x4 is going to be 1/4 t minus 5/4. And then x5 is 7. And now the final step is, let me move this down, is how do I write that in vector notation? And so for those of you who've taken Calc 3, you've seen vectors, and vectors are the exact same, but we're going to do with column vectors. And so the idea is I can actually write down the solution, x1, x2, x3, x4, x5 as a vector. So I'm just going to put boxes on it. So it's like kind of like a matrix, but just a single column matrix. This is our vector. And we're saying that the solution is a sum of actually some vectors. And those vectors have s's times it, or t's times it, or nothing times it. And so breaking it up, the s part is that, and then nothing. And so it's going to be the vector -6, 1, and then there's no s's showing up anywhere else, 0, 0, 0. 1, 0, 0, 0 times s plus, and then the parts that have t's in it, it'll be -3/4 t, 0, there should be an equal sign here, 0, 1, 1/4, and then 0. So we're at -3/4, 0, 1, 1/4, 0, and that's the part that's going to go in t, and then plus the part that has no variables in it, which is 15/4, 0, 0, -5/4, 7. And so this is our solution set. And from this, it's clear that it's a sum of this vector plus this vector plus this vector. And so this vector, you can kind of think about this vector as the starting point. And then this is a vector that goes off in one direction. This is a vector that goes in another direction. So the solution in set is actually a plane, because there's 2 parameters worth of vectors that you can go in. And so the solution, any solution will look like this. And so this is a consistent system and has infinitely many solutions, and actually has 2 directions worth of solutions. And so, and we'll come back to how important this solution set is. But the idea is that this original system we started with right here, if this is the linear system, the set of equations that satisfy this, or variables that satisfy this, is going to have this form. x1 has to be -6 plus some variable, -3/4 plus another variable, plus 15/4. x2 has to have this form, x3 has to have that, and so on and so forth, which is equivalent to saying that its solution set in like a 5-dimensional vector space, since there's 5 components, is it starts at this point, and then it can go in this direction plus that direction. And so that's what a solution set looks like to a linear system in vector notation. And we'll talk more about this vector notation in the next video. Just I want to end real quick with some ideas about existence and uniqueness and a recap. So existence and uniqueness, if you have a linear system, it's consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if the echelon form has no row of the form 0, 0, 0, 0, b. So as long as you don't have a bunch of zeros and a b, you're going to be consistent. And if it's consistent, you either have a unique solution, or you have where there's no free variables, or you have infinitely many solutions when there's at least one free variable. So this would be consistent with infinitely many solutions, so no unique solution. So I'd say consistent, infinite solutions, so not unique. And so how to solve a linear system, you write it in its augmented matrix. So you write down the augmented matrix, you use reduced row echelon algorithm to get it into reduced row echelon form. And then once you're in reduced row echelon form, go back to the system of equations and then find the variable free variables so that you get something like this. And so I'll assign some practice problems for you guys to do this, but that should get you started in linear algebra. All right, thanks.